Okay, folks, we are back, and so we've just finished covering this section, section 4, on linear models for classification, and I thought it'd be useful to just kind of go through what we've covered, touch on some of the key points before moving on to the next chapter. Okay, so what were we talking about? So we're talking about the classification problem. So, our data points are, the data that we're given are going to be kind of samples of, some predictors and corresponding labels. And these labels, they're all going to live in, some discrete set. And there are class labels, and we have these for, xn, yn. And so the idea is that we just want to find some kind of a decision boundary that will tell us how to assign future points based on these learning data, how to assign future points to the appropriate classes. And the type of boundary that we're going to look for in this case is going to be linear in the features or some fixed transformation of those features. So we're going to take our input or the transformation of it and produce some affine linear or affine function of it, and then maybe threshold this or convert it into a probability or something to assign it to the right class. And what this looks like geometrically in kind of the feature space or your predictor space is that you're going to be projecting your, here are all of your points, and maybe these are colored, by the labels, and you're going to be kind of projecting. This is going to be W. You're going to be projecting your points onto some vector that you haven't found, and because of the form of this projection, it's going to correspond to a linear separation in that space. And the question is, how do we find this weight vector? And we saw there's some ad hoc approaches that, let's say, call them maybe not so generously, but some that are intuitive but maybe don't have a probabilistic basis, and then there are some probabilistic ones. So in the ad hoc approaches, one of the things we looked at was, why don't we try just treating these labels that are discrete as just real values, so we can apply our regression, or just solve classification as regression. And you can certainly do that, but what you see is it has certain drawbacks. That, for example, you can take some points. First of all, it's going to be very sensitive to outliers, right? And remember that here all we care about is the class label you assign. So you might have a point that's very, very cleanly, like way over here, so very cleanly out into the positive class, and it's going to carry a lot of weight, despite the fact that you're actually classifying it very well, and you should actually maybe not care about it so much. So in some sense, like the worst problems of regression will start coming to bite you when you try to treat classification as regression. So maybe part of the problem there is that maybe you're spending too much time on these points that you're classifying well. So maybe you should only update your weight vector based on points that you're misclassifying, and that is kind of the approach you take in the perceptron learning algorithm. The idea there is you start with some guess at the weight vector, you look at the points that you're misclassifying, and you adjust your weight vector so that, iteratively for each point, so that you no longer misclassify that point. And if you do that enough times, and there actually is a separating hyperplane, the perceptron learning algorithm will actually converge and find such a hyperplane. So it's kind of an iterative process. It doesn't necessarily correspond. I don't know if it does. I actually have to check this, but it's not so obvious as in the regression case that it corresponds to minimizing some loss function. It's a process that gives you a solution, but at least the loss function, if there is one that it minimizes, or more than one, it's kind of less obvious. And then finally, there was this notion, another kind of intuitive approach. This was Fisher's linear discriminant. And what was his intuition? The idea there was, well, the way you want to find this vector, this weight vector, is such that when you project your data points, onto that weight vector, you want the points to within a class to be kind of close together, and the points in different classes to be as far apart as possible. And so by maximizing an appropriate ratio of those, you end up arriving at a linear function of your data that essentially satisfies that hypothesis or that approach. So those are kind of the ad hoc methods that we discussed, and then we discussed looking at probabilistic approaches. And so there, the idea was that actually let's say that our data are actually being generated. So what are we interested in there? So there we're interested in determining the class label of the kth data point. So we're gonna assume put in some probability structure, and there was kind of two approaches we took to this. One of them was a generative approach. So what we said was, well, okay, so this assignment, well, it's actually proportional to the probability of that data point being generated from a particular class. And you can then compare the probabilities for different classes. And when you look at, if you assume that those classes, if the distribution, the cloud of points for each class has the same covariance, you end up getting the same. So, let's say you end up getting decision boundaries, those linear decision boundaries as well. So, P of x given ck, minus, log of, let's say P of x given cj. If both of these are coming from a multivariate Gaussian with a, let's say, a cluster specific, a class specific mean, but the same covariance, then when you actually look at this ratio, you end up the covariance terms, the quadratic terms disappear, and you get a linear decision boundary. So that's kind of a way of interpreting some of these kind of more ad hoc approaches. You can actually see them as instances of a probabilistic model, and with all the advantages that brings. And the other approach that we talked about, let me add another page here. Was, so kind of in contrast, we said, well, as we saw before, there's this great picture earlier in the book of the problem, this generative approach and how sometimes it can be overkill. You need to actually model all the wiggles of this particular function, modeling distribution of classes of data for each class, where actually what matters is these ratios. And if these ratios are quite clear and quite stark for most of your data points, maybe you don't need to go into all the details of exactly what these individual distributions look like. And so we kind of had the discriminative approach. And the idea here was you just actually model P of ck directly. And we saw that we can come do this using a logistic function. So this is going to be some kind of a sigmoid that then whose parameters you learn from your data. And now then we get into the notion of, and so learning these parameters, and that we arrive at logistic regression, the important concept of logistic regression. So how to learn these weights so that you assign the correct probabilities to the different classes that respects your data. And so we kind of encountered the notion of the cross-entropy loss, which comes up a lot in neural networks, when you actually say, well, what is the probability you gave to a data point, and what was the actual label, and trying to minimize that. That was the cross-entropy loss, so kind of for logistic regression. And a couple of interesting concepts that came up in the context of logistic regression was how to learn these weights optimally, and we encountered the Newton updates. So this is when you use not just the gradient information and gradient descent, but you modify your gradients to take into account curvature and the Hessian of the loss. That's the second order information to potentially speed up your convergence. If your model is actually quadratic, if your loss is exactly quadratic, then it will actually allow you to converge in one step. And when it isn't, well, you can actually maybe do this in an iterative way. And we arrive at the iteratively reweighted least squares. So we saw that you're minimizing this cross-entropy loss using these Newton updates. You arrive at this iterative procedure where you update the weights, then you reevaluate which examples you're misclassifying and by how much, and then you use that to update your weights again, until convergence. And that kind of has a feel of like the perceptron algorithm to it, of iteratively evaluating which points you're getting right and which ones you aren't, and modifying things appropriately. And then we towards the end of the chapter, then we looked at Bayesian logistic regression. And the idea there was, how do we estimate the parameters, and we have to do some kind of some complicated integrals, and then how do we how to do something like predictive, how to do our posterior predictive distributions. so for new data points, so that there's there's some new point that comes in, and you want to get a distribution on on its class assignment. When you integrate over all the weights that you've learned, so you want to kind of integrate out the weights and say, just given all the information I have, what is the probability of the two classes? And there we found out, okay, we have to do these, as usual with the Bayesian stuff, there's complicated integrals. So that led us to the notion of the Laplace approximation, which was, if you have, a big complicated integral that it'll be more complicated than this in high dimensions, maybe you can actually model it as, a Gaussian. And when you have lots of data points on certain conditions, this actually becomes not a bad approximation, because this distribution will actually will tend to converge to a Gaussian. So it might not actually be as bad as it looks. And that gave us some interesting answers, and we kind of also applied it to the model evidence, and we came up with kind of the Bayesian information criterion of how to penalize different models kind of based on the complexities in at least an idealized setting. You should still use cross-validation when you can, but it still kind of gives you some insight into the complexity of different models. So I think that was I think all of the there's lots of points in the chapter, but those were that was the big picture, right? The ad hoc approaches, of which I think the Fisher's is quite a useful one to keep in mind. It comes up all the time in things like linear discriminant analysis, and the perceptron algorithm as well. And then the probabilistic approach we looked at, the generative approach, the discriminative approach, and the discriminative approach, the star of the show is logistic regression, the cross-entropy loss, and then the iterative reweighted least squares for actually learning its parameters. So I think those were kind of the main points in the chapter. I hope it was useful. I definitely found it useful to go over the material. Some of it was new to me, some of it as a refresher, but very useful stuff. And yeah, hopefully I will see you all in the next chapter, whichever one we decide to cover next. Hopefully I will see you there. Thanks.